Today we are going to do the third lab of digital signal processing. Our instructor is Dr. Mohammed Jameel. The objectives of the labs are representation of unit impulse function and unit step function, making unit step function using unit impulse sequence, making any arbitrary signal out of deltas. Now moving to the task 1. In this we have a function impulse sequence which takes the three inputs n0, n1 and n2. n0 is the center point, n1 and 2 are the starting and ending points. We are taking the example here which we have a midpoint of 0 starting from -5 to 5. We are calling the function impulse sequence and plotting the results. After plotting the results we have this output. One is the continuous plot and the other is discrete plot. We also asked to observe by moving the signal to the left, right and scaling it. When we shift the signal to the right by minusing the amount of shift we want to give to the signal, we have that right shifted signal. When we want to shift it to the left, we add the amount by which we want to shift the signal to the left, so we have that output, and at the end we multiply the signal, so we have the scaled output like this. We have the one amplitude there and then we scaled it, so we have the amplitude of 2. Moving to the task 2. In this task we are defining the function of step sequence. This sequence again takes the three parameters n0, n1 and n2. N0 is the midpoint and n1 and n2 are the starting and ending points. We are taking the same example as we did in the last task and seeing its step response now. So when we plot these in the command windows, we have these outputs. One is the continuous plot and other is the discrete plot. For the continuous plot we use the plot command, and for the discrete plot we use the stem command. Moving on to the task 3. In this task we are going to use the impulse sequence function which we already created in the task 1. We have given the signal here sigma k from 0 to infinity with impulse n minus k. When we give that input to the function we created earlier, we have that kind of output. First we have seen its impulse sequence, then we use the sum command to get its step sequence, so we have that step sequence. Moving on to the task 4, we are going to do the same process. We are seeing its impulse and step response by using the same function we have already defined in the task 1. When we give these signal as an input to that function and plot them by using subplots, so we have that kind of plots. First we have the unit impulse sequence, then we have the plot of signal 1, signal 2 and at the end we have the plot of signal 3. Moving on to the task 5. In this task we are defining the function which extracts the even and odd components from the given signal. So to extract the even part of the signal, what does it does that it flips the signal and then adds it to the real signal, and to get its odd part it flips the signal and subtract it from the original signal. We have taken this signal as an example which is varying from -5 to 5 and its values are 1, 2, 3, 4, 5, 4, 3, 2, 1, 0 and -1. When we give this signal as an input to that function which I have already defined earlier, so it displays its even part and then its odd part. Then moving on to the task 6, which is the last task. In this task we are going to do the sampling of the continuous signal. As we know about the Nyquist rate, it is 2 times the maximum frequency or more than that. So we have the signal having a frequency of 1 Hz and we are having the sampling frequency 10 Hz, which is more than 2 times the maximum frequency. Then we are using the impulse train built-in function from the MATLAB to discretize the signal. First we are plotting the continuous time signal. We have this continuous signal. We are going to discretize it by using the Nyquist theorem and multiplying it by impulse train of high frequency. So we have that discrete signal as an output. This is all for the lab 3. Thank you for watching.